Okay, so we start the second session of this mini workshop. The first speaker is Simone Giacomelli from Oxford. Take it away.
Okay, thank you very much for the invitation. So today I'm gonna report the results I found in these recent 4 papers. So I would like to start by thanking all my collaborators in this work. They are listed here. So the idea is to understand superconformal theories from geometry, and I will report some results I found about compactification of type 2B involving S-duality twists, so the so-called S-folds. These have been used to provide the first explicit examples of n=3 theories, which were believed not to exist until not long ago. And since this already gives some non-trivial results from the QFT standpoint, it's an actual question to generalize the construction to less supersymmetric setups and see what kind of theories we get. So in short, we find that by considering the case of 8 supercharges, we can construct all the rank 1 SCFTs, which have been classified recently by Argyves and collaborators. We can directly find arbitrary rank generalizations of these. And another interesting point is the modular space of these theories. The Higgs branch is related to instantons on Lie spaces, but not of the type discussed by Kawamura and Nakajima. So the point is that a crucial step in the construction is the choice of holonomy at infinity for the gauge field. And this can be refined by including outer automorphisms, and here we provide some explicit examples of this. So these results can be used as a starting point to study further these modular spaces. There are several other interesting aspects I will not have time to review, like connections to 1,0 theories in 60, magnetic quivers, holography, and so on. So the strategy is basically to start from the S-folds engineering n=3 theories and combining these with 7 branes with constant axial dilaton. So I will start by reviewing the basic ingredients. So let's start from the n=3 S-folds. So in the simplest cases, we can provide a rather simple QFT interpretation. So let's pick n=4 billion super Young mills. This is the word volume theory of a D3 brane probing flat space. Seen as an n=2 theory, this has an SU2 global symmetry, this SU2F. And what we do now is to gauge a ZL discrete group, which is embedded diagonally inside U1R and SU2F. This naively breaks supersymmetry, but we can remedy this by also embedding ZL inside the S-duality group of n=4. In this way, we can preserve n=3 supersymmetry. So this is just the simplest word volume theories we get by probing with a stack of D3 branes a geometry in F theory of this type, a quotient, a ZL quotient, which involves also the F theory torus. Because of this, L is restricted to be 2, 3, 4, or 6. Otherwise, ZL is not a subgroup of SL2Z. The L=2 case was indeed already well known. This corresponds to an orientifold free plane, and in this case, the theory is n=4. We get O2 super Young mills if we have a single D3 brane. And in this case, we know that this construction can be refined. In particular, we can turn on a discrete flux for H3 and B3 in type 2B. The inequivalent theories we get are two. So one without the discrete flux and one with the discrete flux. And this aspect generalizes to other S-folds, in particular L equal 3 and 4, as shown by Offer and Yushi. For L equal 6, instead, I cannot turn on any flux, so I have only one option. So for L equal 2, 3, and 4, the theories I get, the N equal 3 theories I get, come in two variants. And as we will see, this survives the introduction of 7 branes, which is the thing we are going to discuss next. Okay, so 7 branes with constant axial dilaton. These are classified by codiver singularities. We have 7 non-trivial examples. The various strass are reported here. Here, Z is the coordinate parameterizing the plane transverse to the 7 brane. In general, the presence of the 7 brane freezes the axial dilaton of type 2B to some specific values given in the last column. And these 7 branes support on their work volume a gauge symmetry G and are characterized by a deficit angle. This means that the angular variable around the 7 brane has periodicity 2 pi over delta 7. If I probe this stack of 7 branes with D3 branes, I get N equal 2 theories in 4D, whose Higgs branch is the moduli space of G instantons in flat space. And delta 7 in this context is just interpreted as the scaling dimension of the Coulomb branch operator. Okay, so this is the review of the 2 basic ingredients. Now we are just gonna combine them. This is done essentially by performing a quotient of the various strass I showed before. This is explained in detail in the first of the 4 papers. So the idea is that we let the 7 brane wrap an orbifold space C2 mod ZL, and we combine this with a quotient of the Z-plane. Okay. The important thing is that now, in order to preserve supersymmetry whenever L is not 1, we have to combine this with an SL2Z twist given by Z L delta 7. So now the constraint becomes that L delta 7 should be equal to 2, 3, 4, or 6. Given this constraint, we have the following list of possibilities. So for L equal 1, we are not performing any twist. We go back to the 7 brane case. And these are all the non-trivial backgrounds I can get. For each one of these possibilities, there is an infinite family of CFTs. We can simply construct by probing this space with a stack of these 3 branes. If I start deforming the 7 brane until I remove it completely, I'm just left with the underlying N equal 3 S-fold, and the theories in this case have enhanced supersymmetry. N equal 3, the ones shown in green, and N equal 4 for L equal 1 and 2. L equal 5 is special because there's no N equal 3 counter part of this. It's just purely N equals 2. Okay, so I said that we can deform the 7 brane holding L fixed. This field theoretically, for the 4-dimensional theory, amounts to a mask deformation. So for instance, for L equal 2, I can start from the 7 brane of type 6 then I can deform it to D4, SU3, and then I land on the underlying scaffold, the more supersymmetrical. And here we find the first connection with rank 1 CFTs. We have seen that our geometries are organized according to this deformation pattern. And it's known that rank 1 CFTs are precisely organized in this way. There are two families which really produce exactly this mass deformation pattern. So we can easily match the field theory with the geometry. So one class, which is basically a discrete gauging of the standard one instanton theories, land on S-folds without the discrete flux. Those which are not, the rank 1 theories, which are not discrete gauging of anything, like for instance, the C5 theory, instead can be mass deformed to S-fold with flux. So this ingredient survives the introduction of 7 branes. But how can we understand the discrete flux once I've added 7 branes in the game? Well, the idea is that since we now have a 7 brane wrapping C2 mod ZL, we should also specify the holonomy at infinity. And given that we are considering a ZL orb, it's natural to expect this is going to be some automorphism of Ordevel. This can also be non-trivial as an outer automorphism of Ordevel prime, where L prime is a divisor of L in general. And automorphisms of this form have been classified. So the idea is to start from the twisted affine Dinkin diagram. The twisting is encoded by L prime. And I should start selecting nodes in the Dinkin diagram. The same node can be selected multiple times, such that the sum of the Dinkin labels is equal to L over L prime. So for instance, in the first case, both L and L prime are 2. And so I have only 2 possibilities to satisfy this constraint. Either I pick alpha 0 once, or I pick alpha 4 once. The surviving global symmetry is obtained just by deleting from the Dinkin diagram the selected nodes. So in the first case, I get F4. In the second case, I get SP4, and so on. One can easily check that in all these cases, I have exactly only 2 possibilities up to automorphism of the graph. And this corresponds precisely to cases with and without flux. The theories without flux, I will call them T, and the theories with flux, S. Okay, from the geometric description, we can derive immediately several non-trivial properties of these theories. I would just like to show maybe what we can compute. So we have the global symmetry with the flavor of central charges, and also A and C central charges are computable. The dimension of the Coulomb branch is equal to the number of D3 probes, and the scaling dimension of the Coulomb branch operators are listed here. The global symmetry in general is HT, the group I showed before, times the isometry of the background, the isometry of C2 mod ZL. So SU2 for L equal to, and U1 otherwise. There are enhancements of the global symmetry for low rank, in the case of T theories for rank 2 and 1. In the case of rank 1 theories, this just coincide with the 1G instanton theories. Then let's come to the S series. The dimension of the Coulomb branch is the same as before. The spectrum is almost identical, only the last scaling dimension changes. And here again, the global symmetry is for generic rank, age S times the isometry, and we get announcement in the rank 1 case. Good. So now another thing we can do is to study the moduli space, in particular the Higgs branch, and possible RG flows among these theories. So in particular, we find that for L equal 2, 3, and 4, we have an interesting web of RG flows of this type. So the theory of type S, which is the one corresponding to S-folds with flux, can be Higgsed simply by moving on the Higgs branch to the theory T. In particular, we see that switching off the flux is physically interpreted as an Higgsing. And then I can proceed in this way. The theory T of rank R can be Higgsed to the theory S of rank R minus 1. A nice feature is that the Higgsing T2S is always a nilpotent vev for the global symmetry HT. This makes anomaly matching very effective in the analysis. And apart from this chain of flows, there is another one which is very easy to understand from the geometric description. The CFT point corresponds to keeping all the diffie branes at the fixed point of the ZL action. If I just move them away from this point, but keeping them along the 7 branes, then the diffie branes don't perceive anymore the ZL action, they just see the 7 brane. So all these theories can be Higgsed to the G instanton theories of rank R. This is another RG flow I have, which is combined with this sequence. Another important point is the structure of the Higgs branch. So, as I said at the beginning, we have a parent theory. In the example I discussed before, U1 super young Mills, and then I have a daughter theory, which is obtained with a ZL gauging. Okay, this thing remains true, or at least we find evidence that this remains true for all S-fold CFTs. The models I discussed before, S and T theories, are the parent models. And then I can get daughter theories via a ZL gauging. And it's the Higgs branch of the daughter theory, which has a nice interpretation as moduli space of instantons. This is indeed expected from the geometric description, because indeed, also in this case, we have P-4 branes on top of DP branes, so we do expect an instanton interpretation. Since in this case the 7 brane is wrapping C2 mod ZL, then I expect instantons on any spaces. However, if I just consider the construction by Kronheimer and Nakajima, the holonomy for the gauge field at infinity in the standard construction only involves gauge transformations or inner automorphisms. In particular, the gauge group can be broken by the holonomy, but at least the Cartan subgroup is always preserved. In particular, the rank of G does not change. So if we go back to the analysis of the holonomies, we see here that there are two cases in which the holonomy is trivial as an outer automorphism. So this is for SU3 with L equal to S-fold and SU2 with L equal 3 S-fold. And precisely in these cases, we can notice that both HT and HS have exactly the same rank as G. But this is not true in the other cases. The rank does go down. So this in particular illustrates the point that we can refine the standard construction of instantons on Lie spaces by considering the inclusion of outer automorphism. And from this physical analysis, we can extract some predictions about these spaces, at least the examples we can reach via this construction. In particular, we are able to construct the magnetic quiver and derive the Hilbert series for these spaces. So this is a useful starting point. Okay, this is basically all I wanted to discuss. Let me conclude with a graphic way to visualize the main result. The infinite families of theories we have found are in one-to-one correspondence with nodes of the E8 affine Dynkin diagram. T theories correspond to nodes on the long tail, those in red. So we start from the L equal 1 case, so the standard G instanton theories in flat space. Then we have T theories with L equal 2, L equal 3, 4, 5, 6. Then, as we have said, for L equal 2, 3, and 4, we have a variant of the S-fold construction with the discrete flux, and this corresponds to 2 prime, 3 prime, and 4 prime. And this is all I wanted to say. Thank you for your attention.
Thank you, Simone. We can take a few questions. We have plenty of time. Go ahead, Craig.
Hi. So I actually had a different question, but I have to ask this question about your last slide. What is the significance of representing these in the affine E8 Dynkin diagram?
I kind of expected this question, yeah. So this has to do with the part I didn't have time to discuss in detail, but let me say a couple of words about it. So these models admit an alternative construction as compactification on a torus of a 1,0 theory. Okay. This with holonomies along the non-trivial cycles of a torus. So the 1,0 theories relevant for this game are of very specific type. They are the so-called Orbi instanton theories. So you have M5 branes on top of the M9 wall, which is also wrapping C2 mod ZL. The L is exactly the same as in the S-fold construction. Models of this type are classified again by holonomies for E8 at infinity. The E8s are supported on the M9 wall. Okay, and these again are classified by picking nodes of the Dynkin diagram. So all the theories we can construct by combining 7 branes and S-fold in this way correspond to specific holonomies, which are characterized by selecting only one node once. And I just have all the possibilities.
Oh, that's cool. And actually leads me very nicely into my next question, which is, so you said that all of the rank 1 theories, the rank 1 equals 2 theories produced by this method of S-folds with and without torsion. Is there a counterexample at rank 2 which is not produced in this way, or is it just that the rank 2s are not well enough known to say?
Well, no, I would say I don't cover rank 2 completely. It might well be that this construction can be refined further to accommodate more theories. For instance, I don't find in this class of models, I don't know, SU3 as QCD with 6 flavors. This would be a natural thing to expect. No, I don't get all possible rank 2 models.
I see. Okay, thank you.
You're welcome.
Any more questions for Simone?
Okay. Maybe a silly question, but can you get n=1 theories using this procedure?
Okay, n=1 I haven't explored yet, mainly because in the n=2 case, if you fill in tables like these, you are rather confident you have identified the theory uniquely. In the n=1 case, I'm not so confident about these, but definitely it's possible to do. So, for instance, if you consider all possible quotient operations which are compatible with n=1 supersymmetry at least, you can easily see that you can fit in this construction all the orbifold Calabi-Yau, which in F-theory engineer 6D-dimensional models. So, in particular, the three branes probing this Calabi-Yau should be a particular case of this construction. For the time being, I don't have much to say about these models. It would be interesting to look at. So in the first paper of the 4, we discussed a bit all possible quotients which are compatible with supersymmetry.
But in this other way of compactifying on a torus, do you see what will be the connection there? Like,
so for this class or in general for n=1?
General n=1.
Well, okay, the thing I can say is the following. So if we pick the simplest example, so just the trivial asphalt case, so you just have the 7 brane. Okay, pick a 7 brane of type E8. And okay, the 4D theory living in the on the D3 in this case is known to be E8 Minan-Nemeshansky, which is the double-dimensional reduction of the E string. And this string can be engineered by M5s on top of M9. So you have M5s wrapping the torus. Now, in both the type 2B and M theory setups, you have a C2 transverse to the M5. And the isometry of this C2 just provides the S2 global symmetry of the theory, the S2 are symmetry. And so in order to get the S-fold construction, we want to orbifold this C2 in type 2B, and we just have to do the same on the M theory side. And so under this correspondence, the quotient behaves very well. Okay. And now the subtle point is just to map holonomies, the choice of holonomies on one side to the choice of holonomies on the other. So in this class of theories, this can be done rather in detail, but I expect this to work more in general. So yeah, this is the connection, and probably it can be generalized.
Thank you.
Okay, thank you, Simone. We'll move on.
All right.
Pietro, can you share your slides?
Sure.
Okay, we're happy to have the second talk by Pietro Genolini. Please go ahead. Thank you.
Thank you. Hi, everyone. First, I would like to thank the organizer for the work in creating this series of talks and lectures throughout the year and for the invitation to speak at this workshop. I will talk about some work that I've done in collaboration with Luigi Tizzano, who's at the Simons Center, and is going to speak about something completely unrelated tomorrow. And I'm going to talk about 't-Hooft anomalies. So 't-Hooft anomalies are phase ambiguities in the partition function of a theory in the presence of a background gauge field for a global symmetry. One of the most important features is that they are invariant under RG flow. Therefore, we can use them to explore the phases of the theory in regimes that would be otherwise inaccessible. Now, this has been known since the 80s and used very successfully. However, recent developments in the study of the symmetries of a theory have showed that it's very important to include also subtler anomalies involving discrete symmetries and higher form symmetries, which act on extended operators. And these tools have been mainly employed to study field theories in dimension equal or lower than 4, but they also apply to field theories in dimension higher than 4. Now, from perturbation theory, it would seem that those are trivial since there are no relevant interactions that you can add to the free fixed point. However, one of the great results of string theories in the 90s has been the construction of intrinsically strongly coupled superconformal local theories that can be deformed and are connected via RG flow to the standard description in terms of the n equals to 1 super Yang-Mills theory, possibly with some matter. Now the question for today is, what can we say about the symmetries from the infrared? So, and are they anomalous? And if so, can we use these anomalies to say something about the dynamics? And before diving heading into supersymmetric theories though, let's look at a less symmetric cousin, which is 5-dimensional pure Yang-Mills theory, which we view as an effective infrared theory with a UV cutoff. I work with SUN for simplicity, but the discussion can be extended to different gauge groups. Now there is an abelian zero form symmetry. The objects charged under this symmetry are disorder operators that correspond to boundary conditions for the gauge field at the insertion point of the operators. If we surround the insertion point with a force sphere, we see that the charge is just the instanton number of the configuration, which gives the symmetry its name as the instanton symmetry. Furthermore, we notice that the current, which is star trace F wedge F, is conserved just by virtue of the Bianchi identity, without the need to resort to any equations of motion. Moreover, since the only field in a field theory is the gauge field, which is trivially in the adjoint, there is also a Zn center symmetry. It is a one-form symmetry in the sense that the charged operators are extended objects, namely Wilson lines that are simply multiplied by a nth root of unity as I act with a symmetry on them. In order to keep track of global symmetries, it's very useful to introduce background gauge fields. For U1, for the instanton symmetry, we do so by simply introducing an abelian connection and coupling to the current in the minimal way. And we see immediately that there is no 't-Hooft anomaly associated to this symmetry. Upon performing a large gauge transformation for the background gauge field by a closed but not exact one form with a winding number L, say, on the circle, the partition function of the theory changes by a phase that is just trivial because it contains the product of L, which is an integer, and Q, which is an integer by construction. Now, a different story happens when we turn on a background gauge field for the center one-form symmetry. Turning on a background gauge field for the Zn one-form symmetry means including in the path integral gauge configurations for the quotient group PSUN with Brouwer class fixed to be equal to the gauge field B. The Brouwer class of a PSUN bundle is the analog of the Stiefel-Whitney class for a SON bundle. now the explanation is relatively simple. There are more PSUN bundle than there are SUN bundle, and some of them cannot be lifted to be SUN bundle because they fail the co-cycle condition. This lifting obstruction is encoded in the Brouwer class. If we want to be even more concrete than this, another way of saying this is that for these bundles, the instanton number may be fractional, and the fraction by the Brouwer class. In fact, it's measured by the Pontryagin square of the Brouwer class, but it's irrelevant, the precise definition. The important point is that it's an element in a discrete group. The crucial point of this, though, is that in the presence of a non-zero background gauge field for the one-form symmetry, the instanton number may be non-integer, and therefore, upon a large background transformation for the instanton number, now the partition function picks up a non-trivial phase that cannot be removed by a local counterterm. So this is an 't Hooft anomaly. In fact, it's a mixed 't Hooft anomaly between the instanton symmetry and the center one-form symmetry. Now I will take a minute to recall some of the properties of 't Hooft anomalies. 't Hooft anomalies do not invalidate a symmetry. A symmetry with an 't Hooft anomaly cannot be gauged, but it's still a global symmetry of the system. However, mixed 't Hooft anomalies do imply that if you gauge one of the symmetries, then the other is explicitly broken. The most crucial fact for the purposes of this talk for 't Hooft anomalies is that they are stable under RG flows. And finally, in the modern interpretation, which stems from condensed matter, an 't Hooft anomaly can be interpreted in terms of, do you see if I write on the, can be interpreted in terms of inflow from a field theory in one higher dimension. Okay, so now that we have showed the existence of an anomaly and described some of its features, it's time to look at the consequences for the dynamics. First, we notice that since the anomaly involves an higher form symmetry, it remains an anomaly when it's reduced on a circle. This is particularly useful if we are interested in describing the behavior of 5D Yang-Mills theory at a finite temperature. As we reduce down to 4 dimensions, we find a non-trivial 4-dimensional anomaly for the effective symmetry group U1 minus 1 times Z0 times Z1, where the first factor corresponds to the periodicity of the axion that comes about from the reduction of the background gauge field. And the next two factors Zn correspond to possible positions of the Wilson lines charged under Zn. Either they can be placed either along the reduction circle, so they correspond to local operators charged under Z0n in 4 dimensions, or they can just live on the R4 factor and they remain lines. Now, the presence of an anomaly means that not all symmetries can be preserved in a trivially gapped vacuum. At low temperatures, when the radius of the circle is large, the 5 description is good, we expect deconfinement, which is compatible with saturating the anomaly in a vacuum in which the U1 minus 1 is preserved together with the Z0, but Z1 is spontaneously broken, signaling exactly deconfinement. At high temperatures instead, we can work in the 4-dimensional effective description. And now there are distinct vacua for the effective potential for the adjoint scalar coming from the gauge field reduction. And this signals the breaking of Z0n, whereas the anomaly is saturated by a vacuum where U1 is preserved and Z1 is preserved, which is perfectly compatible with what you expect. And in fact, it puts it on a firmer footing, which is that gauge theory in 4 dimension confines. Now, before moving on to the supersymmetric case, I should mention one last consistency check that can be obtained by considering the reduction with a fixed chemical potential. So it's a different ensemble. So we fix the holonomy of the background gauge field around the S1. And in this case, the minimal coupling reduces to a 4-dimensional theta term where the periodicity of the theta angle comes about from the periodicity of the axion. And the 5-dimensional anomaly reduces to an anomaly in the space of coupling constant, as described by Cordova, Friedland, and Seiberg, or equivalently as the anomaly between the center symmetry and time reversal for 4-dimensional Young Mills described in TTT, Gaiotto, Kapustin, Komagotz, and Seiberg. Now, okay, having introduced this anomaly in the case of pure Yang-Mills theory, now we complete the vector field to the full 5-dimensional vector multiplet and obtain a supersymmetric theory. This requires adding a real scalar and symplectic Majorana spinors in the adjoint representations of the gauge group and auxiliary fields, but they are irrelevant for our purposes. We still have the instanton symmetry because the conservation only depended on the Bianchi identity, but not on the equations of motion. In addition to this, there is also a zero form at SU2 zero form for the R symmetry, for the canonical R symmetry of n equals to 1 of 8 supercharges. Now the additional fields in the vector multiplet do not break the center 1 form because they all transform in the adjoint. Therefore, the mixed 't-Hooft anomaly that we described for pure Yang-Mills theory is still there in the supersymmetric case. However, the new aspect here is that, as we mentioned at the beginning, string theory tells us that now there are non-trivial interacting superconformal theories that are connected to super Yang-Mills by RG flow. Moreover, the global symmetry is often enhanced at the fixed point, and the deformation starting the RG flow is an explicit breaking of this enhanced symmetry. For concreteness, in the following, I will focus on the case of SU2, super Yang-Mills with center Z2, which is supposed to be UV completed to an interacting superconformal theory with a zero form algebra SU2R times SU2, which I write E1 because I know where I'm going in five slides. And now I would like to know, what does the anomaly, the infrared anomaly, imply for this case? On the Coulomb branch, which is isomorphic to R, we break the non-abelian gauge group to its abelian subgroup, and we are in a Coulomb phase. The instanton symmetry is preserved, whereas the Z2 center symmetry is broken, and we see it explicitly by its nonlinear action on the abelian gauge field. Now, if we assume that the one-form symmetry is not accidental in the infrared, we can hope to say something about the ultraviolet, where we know that there is a gapless fixed point. The simplest case is that the infrared anomaly is matched by a vacuum where the one-form symmetry is spontaneously broken and the zero form is preserved. However, there is another interesting possibility, that is that all the symmetries are preserved and we match the anomaly. In this case, though, if anomaly matching works in the standard way and there are no novel mechanism, then we can say something about the global structure of the global symmetry group at the UV fixed point, because it has to be an SO3 in order to match the anomaly, simply because SU2 doesn't have a degree 2 characteristic class, an SU2 bundle. Yes. Now, it would seem that it's never possible to find a case where the instanton symmetry is spontaneously broken. In fact, this is not possible in the gauge theory phase. This is because in order for U1I to be spontaneously broken, the instantonic particles, which are charged under it, would have to be massless, but their mass is proportional to the inverse gauge coupling. And therefore, it's never possible to break the instanton symmetry at weak coupling. However, it is possible to break it on the Higgs branch that emanates from the UV fixed point, as was showed by Cremonesi, Ferlito, and Ani Mekareya. The presence of a Higgs branch in a pure super Yang-Mills theory is surprising, but it's due to the presence of massless instantons in the UV. In fact. Now, further information about the interacting fixed point may be gathered using large N methods and holography. We can't apply those to SU2 gauge theory, but so we consider a slightly different model. We consider as super Yang-Mills with a symplectic gauge group. The anomaly is still there, as we'll see in a second. And we also add an hypermultiplet in the anti-symmetric representation, so we add some matter. We still have the canonical R symmetry, we still have the canonical instanton symmetry. And also we have an SU2 or SP1 flavor symmetry that rotates the hyper. The crucial feature of this model, though, is that the one form symmetry is not broken by the presence of the hyper because of the particular representation that we've chosen. Therefore, the mixed Haupt anomaly that was described earlier still holds. Moreover, for any n, this theory is supposed to be connected by RG flow to an interacting superconformal point, that, as was shown by Intelligator, Morris, and Seiberg, and the enhancement of the symmetry is again U1 to SU2. In this model, the novelty is that we can use supersymmetric localization to compute the vacuum expectation value of Wilson loops charged under the one form symmetry. And we find that it's non-zero. These are BPS operators. So if we assume that there are no contribution from irrelevant operators at the fixed point, we can take the computation that we have done in the gauge theory phase and assume that it gives us the same result as the VEV of the line defect of the superconformal line defect at the UV fixed point. Because the line operators are order parameters for the one form symmetry, and they have a non-zero value, this signals spontaneous breaking of this symmetry, which is compatible with the scenarios that we illustrated from anomaly matching. Furthermore, we can also compute the VEV using holography. The same model is holographically dual to anti-de Sitter backgrounds in massive 2A, and the computation in the large n limit agrees with the computation of the dual gravity observable, which is just a fundamental strain stretched in ADS. Finally, let's go back to our simple SU2 model, but now let's add matter. As long as we add less than 7 hypermultiplets in the fundamental representation, we still have a UV completion to an interacting SCFT, and string theory predicts also the global symmetry of this fixed point, which is enhanced from the symmetry in the infrared. Namely, the instanton symmetry combines with the flavor symmetry into a ENF plus 1. So that's until E8. And then you go into affine algebras and you uplift to 6 dimensions. This enhancement has been checked in various ways with various field theoretic methods, and it's a solid prediction from also from infrared, not just from string theory, not just from geometry. But the important point for us is that the center symmetry in the infrared is explicitly broken by the presence of matter transforming in the fundamental representation of the gauge group. So we cannot have our favorite mixed Haupt anomaly between the center symmetry and the instanton symmetry. Nonetheless, we can apply to this theory techniques that were originally used for quantum chromodynamics and construct a non-trivial anomaly between flavor symmetry and the instanton symmetry. Indeed, we observe that the global symmetry group that acts faithfully on the theory is not the flavor symmetry group, because some of the transformations of the flavor symmetry group can be undone by a gauge transformation. Therefore, there is a quotient by the center of these two. Thus, the bundles of the two symmetries are locked together. Because of this, it is possible to include in the path integral SO3 gauge bundles by cancelling their obstruction with a Stiefel-Whitney class of SO bundles for the flavor symmetry. However, as in the previous case, the presence of SO3 bundles makes the instanton charge fractional, spoiling the invariance of the partition function under a background transformation for the U1. Therefore, we have a mixed Haupt anomaly between the instanton symmetry and the flavor symmetry. What can we conclude about the phases of the theory? Now, on the Coulomb branch, the situation is the same as in the previous case. U1 is preserved because you see that there are objects charged with any charge. However, we can explicitly break spin to NF to U1 to the NF by turning by turning on masses for the quarks. In the UV, the anomaly does not provide any information about the global structure of the symmetry group. Indeed, using field theoretic methods, localization of ray operators, Chang and O have showed that the symmetry group in the ultraviolet is the simply connected group with algebra ENF+1. So the gapless phase can then match the anomaly. Moreover, surprisingly, as in the case without matter, global symmetry is spontaneously broken on the Higgs branch emanating from the UV fixed point, thus saturating the anomaly matching, as showed by Cremonesi, Ferlito, and Ani Meccarelli. And with this, we conclude this super quick discussion of some aspects of symmetries in 5 dimensions. We described a mixed Toft anomaly between the center one-form symmetry and the instanton symmetry. So we used something new to learn about gauge theories. We used this anomaly to put on a firmer footing the expectations for the behavior of pure Yang-Mills theory at finite temperature and confirmed the expectation from lattice computations. We then introduced supersymmetry in the game in order to remove the UV cutoff. For SU2 super Yang-Mills, we surveyed various dynamical scenarios and showed that the naive prediction would be that the one-form symmetry is spontaneously broken at the UV fixed point. And we showed that this is compatible with the expectation from holography and large N for a different model, but with a similar features in the sense that the global symmetry enhancement was analogous. Now, this last point is crucial. So most of what we said only required analysis in the infrared toolkit of gauge theorists. However, string theory, as we said in the beginning, has provided crucial insight into the structure of strongly coupled theories in dimensions higher than 4 and 4, as we saw in the past 4 talks. And there have been various developments in the past few months studying higher form symmetries from geometry. It would be, it's then relevant, super relevant, to connect the results obtained using a field theoretic approach in the infrared, as I just described, with the insights obtained using string theory compactifications. With this, I conclude. Thank you very much for your attention.
Let's thank the speaker. And then we can take a couple of questions. Okay, I have one. In the comparison with holography, so the UV theory, the one form, the center symmetry is spontaneously broken, but there should be a way to still read off that this anomaly is there in the bulk. Can you do that?
Yes, so that's a very good question. And it's something that we're currently thinking, also prompted by discussion with other groups. Indeed, if the symmetry is spontaneously broken in the UV, you would expect some mechanism that saturates the anomaly. We haven't yet found one. Of course, there is another possibility, which is that this is an accidental symmetry in the infrared.
Yes, indeed.
So yeah, I would like to know the answer. I'm currently thinking about it.
Okay, I'd be curious to discuss more.
Yeah, thanks.
So we had one question. Joe Minahan, I think, have a question. Please go ahead.
Yeah, I had a question. So best I can tell, the arguments in the infrared would still be true for 5D n equals 2, that there's still like a mixed Toft anomaly and everything like that. Is that true?
Yeah, I think so. It doesn't require, yeah.
So can you say anything then about going to the UV, and which presumably is like some 60-20 theory?
Yeah. No, I don't know. I have not thought about it. It's true, it goes to 60. And then there is there's a lot of recent work by, well, Ken, Cordova, Dumitrescu, and also Pruzzi et al. On one-form symmetries. Yeah, I don't know. That's a very good question.
Okay, thanks.
Thanks. I'm sorry that I can't answer these questions. They're very good questions. I wish I could answer them.
Do you understand what the effective 5D theory looks like?
In n equals 2?
Mm.
Well, in the gauge theory phase, it's n equals 2.
No, the bulk theory that gives you the ADS6 vacua dual to the system.
Oh, you mean F4 supergravity, like Roman supergravity in 6 dimensions?
Yeah, in particular the truncation around this vacuum.
Yes. So the F4 like F4 Roman supergravity has been studied. You can compute the fundamental string, but then in order to match the anomaly, you would presumably need the full string theory, because you would need something, some string also, probably also in the internal space.
Yes.
The S4 orbifold.
Yes, that's right.
Yeah.
So, yeah. So there is a question by Sergey. Please go ahead.
Yeah, I wanted to clarify something quickly. Thank you for a very nice talk, by the way. When you're listing different options for supersymmetrizing SU2, how does one rule out TQFT that saturates the tooth anomaly?
Yes, that's one possibility. So there is a possibility, that is that in the UV, there is an additional TQFT that is, so it's a UV TQFT, right? So it would have to be interacting in some way, but then somehow decouple in the infrared. Okay, so sorry. So it's true that it could be a TQFT because this is a finite anomaly. So it's not prevented by Coleman-Grossman to be saturated by TQFT. It's just hard to imagine where it could be apart from the Higgs branch. So probably it's a description on the Higgs branch, I guess, I would say. Otherwise, it's a TQFT that is coupled in the UV because it saturates the anomaly, but then in the IR, it somehow decouples. That's everything I can say.
Thank you.
Thank you for your question.
If there is no more questions, we can put the slides up for the next talk. Thank you.
Thanks.
Jingxiang, are you here?
Yes. Let me put the slide.
Good. Okay, good. We start the last talk for the session today. Jingxiang Wu from Perimeter. Please go ahead.
All right. Thank you very much for the kind invitation and for organizing such a wonderful conference, wonderful seminar series and of this workshop. And so today I would like to talk about the research I did with David Gaiuto, Jihong Li, and Benoit Vicedo, based on the following 2 papers that already appeared. So the goal of this talk is trying to tell you the relations between the following 3 stories. The Kondo defect is a particular type of defect in 2-dimensional conformal field theories. And ODEM correspondence is about the studies of Stokes data of ordinary differential equations. And 4D Chern Simons is a particular 4-dimensional gauge theories that is quite unusual and recently studied a lot. There's actually another one called the Ivan-Godin model, which is also crucial for us, but I don't have time to talk about it today. All right, so Kondo defect. So how do I define the Kondo defect? So let me give you the example of chiral SU2 level K WW model, although the generalizations to other rational CFT should be straightforward. So it's very similar to what you do in Wilson lines in gauge theory. So you take a trace of a path order exponential, and inside the integrand, we take the chiral part of the WW current, contract it with a bunch of matrices, and where I take the matrices to be the representations of SU2. And I will label this by the dimension of the representation, n, which is an integer. So the G here is a marginal coupling. So it was shown by Bashas and Gabdiou that this defect can be quantized nicely, in the sense that there exists a choice of renormalization scheme such that the following symmetries are preserved. There's a translation symmetry along and normal to the defect. There's a chirality, meaning it commutes with the anti-chiral current. There's also a global SU2 symmetry. So this G is classically marginal, and you can start the beta function. And it turns out it is asymptotically free in the UV. And as you go to IR, the coupling increase, and it's strongly coupled in IR. And as you see in the generical case of asymptotic freedom, there's a dimensional transmutation, which means the coupling is turned into so the dimensionless coupling is turned into a dimensionful scale, which I will label by the e to the theta. Okay, so instead of, so we have a one parameter family of this Kondo defect, and instead of label the defect by the coupling, I will instead use the scale theta here. Okay, so here is the result from the perturbation theory in the UV, and we actually know a lot more than this. For example, there's an interesting result from Alpha and Ludwig that tells us, although it's strongly coupled in the IR, we know what is an infrared line defect. So it turns out it's quite rich, and when n is smaller than k plus 1, what you get is a topological line defect. And it's one of the Valente lines. Let me recall that there are k plus 1 Valente lines in SU2 level K WW model. And I will label this by this curly L with the subscript n. And this n takes values from 1 to k plus 1. But when n is bigger than k plus 1, the situation is very different. You have a k plus 1 Valente line, but you still get infrared Kondo defect, but with fewer spin. Moreover, this Kondo defect is believed to be integrable in the sense that the following relations are satisfied. And so, for example, different Kondo defects will commute with each other. And there's also fusion relations, often referred to as Hirschhart relations. So we check these relations as operators up to order G to the 4, and they are satisfied. So to sum up, Kondo defect is an interesting class of defect in 2D CFT that interpolate between topological defects. And more importantly, they carry the integrability structure of the bulk CFT. But clearly, perturbation theory is not the best tool to study the Kondo defect here, because it's strongly coupled in the IR. And also, if you look at the Hirschhart relation, and here I really want to shift the theta in the imaginary direction. So somehow I want to study this Kondo defect with complex theta, which is not very natural in the defect language. That will bring me to the next topic, which is called ODEM correspondence. So it's quite a mysterious relations. And so let me give you this rephrase in the language of Kondo defect. So if I give you a CFT, you can define the Kondo defect. And as the operators acting on their Hilbert space, you can calculate the expectation value. So the statement of this correspondence is that this expectation value can also be obtained from a ODE. More precisely, it's a Stokes data of this ODE. The mysterious part is this ODE at first sight has nothing to do with the conformal field theory. So let me illustrate this with the example we propose in the paper. So the claim is that for the chiral SU2 level K WW model, the ODE is as follows. So it's a second order differential equation in the variable X. And here is the potential part that has two parameters, theta and K. So K is the level of the WW model, and theta is a parameter. But I want to later I want to identify with the theta I defined earlier in the Kondo defect. And let me just put T of X to be 0 for now. So this is the second order differential equation. You can solve it, and I want to look for the solution, which I call psi 0, that is a unique one up to normalization that decays exponentially as you go to positive infinity. So you have that solution, and you take that solution, you shift the theta parameter by this amount and by an opposite amount. Now you have two functions basically, and you calculate the Wronskian between two functions. The statement is that this Wronskian will match the expectation value of the Kondo defect. So this is this equal sign is the claim. So what about other states in the spectrum? Meaning, like, what if I consider a different state and the expectation value in that state? In this case, the techniques is the idea of to do so is already appeared in the literature. Basically, what you have to do is try to add extra regular singularities of trivial monodromy. And let me parameterize this T as a squared plus partial A, where A is as follows. So now the idea is try to fix the parameter here, and in particular, the location of WI and WA, such that the ODE has trivial monodromy around those singularities. I will not bore you with the details, but the punchline is you can do this. And once you do this, you just find out what is the small t of x. And now you go back to the ODE and you find the solution psi 0 again, and you calculate the Wronskian. And now that will give me the expectation value in that particular state. Okay, so I haven't told you how we wrote down this ODE. And in fact, I will leave that question to the next section, but let me just say that the physical meaning behind this correspondence is still unknown. For now, let me suppose someone hand you this ODE, and what you can do is try to do some calculations to verify the claim. And indeed, we did a bunch of explicit calculations, and listed here, and it's true. And but after we are confident this claim is true, we can use the ODE to learn the physics of the Kondo side. This is because in practice, whenever you can do calculations on both sides, the Kondo side and the ODE side, most often you can, the calculations on the ODE side is much easier than the Kondo side. And so, and moreover, there's sometimes you can do some calculations on the ODE side, but that is not accessible from the Kondo side. Let me give you this example of the second point. Okay. So here's the result. So we can do some kind of analysis called exact WKB analysis that already appeared in earlier talk by Aona, I think. So you do the exact WKB analysis to the ODE, and you can map out this diagram. So this is on the theta plane. And here is a real axis. And remember the RG scale, lambda is e to the theta. So the real axis is my RG scale. And here is a UV, and here is a IR. This is the RG flow direction. The result of this analysis, if you look at here, is basically tells me if I start with the Kondo defect in the UV, in the IR, I would find the topological validity lines labeled by the subscript n. Okay. So this confirmed the conjecture from Effler and Ludwig. And we can actually do much better than this. For example, you can turn on some small imaginary part. And turns out in the IR, you still get validity lines, the same one. But if you keep increasing the imaginary part, what you get is a different infrared line valued in this strip, in this one. So this is a line of phase transition. In fact, you get a sequence of phase transitions until you reach, you get back to the original Kondo defect in the IR. And this will be one of the examples of work crossing phenomena. Here, this diagram is when n is smaller than k plus 1. As I reviewed earlier, the situation is a bit different when n is bigger than k plus 1. But again, along the physical RG regime, we can still confirm the conjecture from Effler and Ludwig and map out the entire infrared diagram for all the complex theta. So this is the example we can do on the ODE side, and I hope I can use this example to convince you the ODE can be very powerful in the studies of defect. Now let me just return to the question how we wrote down this ODE. And that requires us to understand what is the physical meaning behind this correspondence. To answer this question, we use a recently proposed theory in 4D called 4D Chern Simons. So I guess it might not be very familiar to people. So let me just quickly tell you what it is. It's very simple, actually. So it's like a 4-dimensional version of 3-dimensional Chern Simons. And here the space-time is R2 times C. I take the coordinates of C to be Z. And the action is basically the Chern Simons 3 form, the usual one, and you wedge a holomorphic 1 form, dz. And it was shown by Costello that the theory admits a nice quantization. So it's valid to all orders in perturbation theory. Also, it has nice property that it's topological along the R2 direction. That's why it's often called topological plane. And it's holomorphic along the C direction. And C is called a holomorphic plane. So how do we construct the Kondo problem in this case? To do that, let me insert the surface defect along the R2 direction. So the XY is a coordinate along the R2 direction, and we put a surface defect on the surface defect, I put a chiral WW model and I couple it to the Bow gauge field via this coupling. It located at a fixed position along the holomorphic direction. Then I put a Wilson line in the bulk at another fixed holomorphic direction. There's one thing you have to be very careful about, which is the gauge anomaly, because famously, if you try to couple the chiral WSW model, there's a gauge anomaly. And to cancel that gauge anomaly, we have to use a different one form. So here, when I define this foundation Simons, use this one form DZ. Now I want to replace this with a different one. When you do this, the foundation sum is not gauge invariant anymore, but the new gauge anomaly you introduce will cancel the gauge anomaly from this coupling. And now you get a theory free of gauge anomaly. Now we want to do the RG transformation in this case. And it was shown by Costello very recently that there exists a choice of renormalization scheme and a choice of gauge such that when you do RG flow, the position of the surface defect doesn't change, but you move the position of the Wilson line. More precisely, you shift a theta parameter, which the theta is defined as a primitive of this one form. Okay. So in the UV, it's a wave, it's very far away from the surface defect, but in the IR, they are very close. So now we have all the necessary ingredients to understand this setup. Most of the properties we find mysterious are quite automatic in this construction. For example, the commutativity of the line defect is just come from the fact that you can commute the Wilson lines in the bulk, because if you have a second Wilson line here, they are located at different positions along the holomorphic direction. And you can commute them without any difficulties. Oh, sorry. The Hughes relation is basically coming from the fusion relations of the Wilson lines in the bulk. We can also talk about the beta functions. Let's just try to figure out what is the relation between the coupling and the scale, right? So to do that, you figure out the leading order classical interaction, and that is mediated by this gluon exchange. And that will give me this term in action. So now it's very natural to identify the coupling with 1 over the distance, because recall that the Kondo defect is defined by this. Once we made this identification, along with the previous result here, we know the relation between the G and the scale here, and that will give us the beta function. So these are the checks we did. We can verify the claim. This is the faulty construction, and we try to integrate out the holomorphic direction, and we get the 2D theory. The 2D theory is precisely what we want, the 2D chiral CFT with a Kondo line defect inserted. And the holomorphic direction you get rid of will give me the spectral parameter, theta. So in this framework, the integrability become quite intuitive, and you can understand a lot of things. How about the ODM correspondence? For that, let me give you this conjecture. So to write down this ODE, basically what we want is try to figure out what is capital P of X, because as I said earlier, the small t of X control which excited state you are picking, And that construction is automatic once you figure out what is capital P of X. And the conjecture we made is the P of X is related to the holomorphic one form omega z, which I used to define the 4D Chern Simons by this simple relation. So now the idea is once you have a Kondo in CFT, you find the 4D Chern Simons construction, which give me this omega z, this one form. Now with this omega z and with this conjecture, we can figure out what is P of z. Now we know what is this ODE. But this identification is quite non-predictive in its nature. So we were not able to prove this in the framework of 4D Chern Simons. We believe one has to go to the string theory construction in order to show this, in order to prove this conjecture. So before I conclude, let me give you this simple, one of the first simple generalization you can do, also as a way to refresh you what I talked about. So on the Kondo side, if we are considering like instead a product of SU2s, the Kondo defect is basically you have current and you have a coupling for each SU2 factor. The corresponding ODE is also very simple to write down by using this conjecture here. So you just have, before I have this e to the 2x and x to the k. Now I have one factor for SU2, for each SU2, so I have a product of zeros. The construction in 4D Chern Simons is also very simple. So before I have one surface defect, now I have multiple surface defects, each located at different positions along the z direction. And the Kondo defect is coming from one single Wilson lines in the bulk. The corresponding twisted one form is here. So conclusions. So I told you about this relation between three different stories and Kondo defect in CFT. The ODE mathematically is often called FN-OPER, 4D Chern Simons. If you do the calculations in practice, the calculations is often easier on the ODE side. So we can use ODE to understand the physics, understand some new physics of Kondo defect. And the integrability feature, among other things, can be made very intuitive in the 4D Chern Simons construction. So in particular, using these calculations, we can study some wall crossing phenomena in the IR that is not accessible from other techniques, for example. So about the physical origin of this ODIM correspondence, we made that conjecture, but to actually prove that conjecture, we have to go to the string theory construction of 4D Chern Simons. And that will be one of the future directions. But the idea is try to realize this as string dualities. Okay, so future directions include, for example, try to generalize. So here I'm talking about the SU2s or product of SU2s. And you can try to do more general Lie algebras. On the ODE side, we have to try to study the spectral network with more generic Lie algebras, and that is not well understood yet. On the Kondo side, there's also interesting complication as well. You can also consider coset. That will give me minimal model, for example. If you break the SU2 global symmetry, that will give me an anisotropic Kondo problem. A more drastic change you can make is try to replace the CFT into a massive integral model. And that will, instead of considering OPER, will like we will need to consider the Hitchin system, which is a PDE. And lastly, we really want to understand this ODEM correspondence from the point of view of string theory construction. With that, let me just end here and thank you for your attention.
Let's thank Jingxiang one more. Are there any questions? You can just go ahead and unmute yourself.
I have a question.
I have a quick question. Is it important that the CFTs are actually rational CFTs that you're looking at in SU2WW? Could you do this also for SL2R?
Yeah, that's a very good question. So here the Kondo defect are thought of as a carrier of the integrability structure. I'm not entirely sure if the integrability is still present in the irrational CFT. If it is, then I believe so.
Yeah, so I just know, so in the context, right, that Gabardie and Bachas were studying this, you could think of, right, it's a deformation of the boundary CFT of the WW model. Yeah. So in that context, just I'm asking whether you know that that also worked for non-rational theories. If you don't, it's fine. Let me ask another question. Can you say a bit more about the string realization of the whole construction?
Sure, yes. So there are already some proposals of the Chern Simons, and basically one of the idea is try to generalize the Witten's 5-brane system. So the D3 NS 5-brane system will give us the analytic continued Chern Simons theory. So you can find the analytic continued Chern Simons at the boundary of D3 branes. And the idea is try to do the D4 NF 5-brane system. And on the boundary, with some twist, on the boundary, you will find the 4D Chern Simons. This has already been started by a group, 10 and some other people, I don't remember. There's also a construction started by Costello and Yagi that use the D5 brane system. This will give you the 6D 1,1 theory. So then you turn on some topological twist, and so you have, for example, if I have R2 times C here. C is my so this is a spectral curve, and I turn on the topological twist in these 4 directions, and now I turn on the omega deformation in this 2. So I will get rid of these 2 dimensions. Now I go back to the 4D Chern Simons. So there are multiple string theory realizations, but how do we find this, the twisted one form is still eluding us.
Thanks.
I have a question.
Sure, yeah.
In the last setup from the 6D 1,1 theory, the surface defects appearing in this talk, where do they come from? Which defects are they coming from?
I think there are some choices you can do. Well, I think that is one of the central questions, I guess. I think you can make some choices, but it's not clear which one will give me the desired construction that automatically give me this one form.
Thank you.
I have a question.
Sure, yeah.
2 questions actually. One is, what if you want to study a non-chiral CFT? You have to use 2 Chern Simons.
Yes. So that is this part. In the CFT, sorry, in the 2D story, and you can do that. That basically try to, so in the bulk, you have integral model and you have a Kondo defect here. And basically you have to use J and J bar. So you have two in your line defect. For the ODE side, what you do is you do a PDE, which is given by Hitching system. For the 4D Chern Simons part, so instead of adding a chiral defect, you consider the anti-chiral defect. And the idea is once you get rid of this transverse direction, this will, like the chiral and anti-chiral will couple together. So one of the natural theory to study under this construction would be Grosvenor-Ville model, chiral Grosvenor-Ville model, which is like a WW model plus some JJ bar deformation.
Mm-hmm. And another question I had is, why can you encode the excited state in just one function? What is the information about the operator that is creating the excitation?
In which part?
So in the differential equation, there is a function t of x, which you say it encodes the excited state.
Yes.
But it has no information about which operator is creating the excitation. I mean, you have different primary fields. You can have states associated to different primaries.
Oh yeah. So by excited state, I mean this. So suppose so this is the CFT part, right? So I consider this CFT on the cylinder, and I put my Kondo defect along the spatial circle, for example. Then I put a state here. I put a state here. I can calculate the expectation value. The statement is that this will be given by the Stokes data of a different ODE. It's like adding extra singularities to the vacuum opera.
I see. Okay.
Yeah, but it's a very interesting question. I think open question to understand excited state in 4D Chern Simons. I don't believe it's possible. That's why to really study in detail the string theory construction would be useful.
Thank you.
I have a simple question. What was the original motivation for this ODE-IM correspondence? Like why it came up about?
So I'm not exactly sure. I think it's coming from studying the spectral theory of ODE, and they define some object called spectral determinant. So if I give you ODE, and you can define some spectral determinant. And what they found is that the spectral determinant happened to satisfy some functional relation. And that functional relation is exactly the same as what people found in the integrable system. So there is this
so it's an experimental mathematics thing.
Yeah.
Okay, thank you.
I have a question.
Sure, yeah.
So in your 4D Chern Simons theory, instead of doing the standard ADA Chern Simons, can I consider a more general 3D topological theory? And if so, what sorts of constructions can you make? Or even can I generalize this to other dimensions where you have other sort of types of Chern Simons couplings that you can add, for example, in 6D or in 4D where you have BF type constructions and so forth?
Yes, that's a good question. So I'm not sure, like, try to replace 3D Chern Simons to a more general TQFT would be a very good starting point. But but there's a thing you can study, for example, so you can think of this 40 Chern Simons as a halfway between the 3D Chern Simons and the more familiar holomorphic Chern Simons in 60. Mm-hmm. So there you have a three form, right? You have a three form wedge Chern Simons three form. So it's like a halfway between. So from this point of view, you can also try to study a 5D Chern Simons, which is holomorphic in some directions, topological in some other directions. Yeah, so it'll be interesting to ask similar questions. But the why people are interested in 40 Chern Simons is it precisely give you the higher dimensional realization of integral models. So the 2 dimension here will give me the space-time of 2D, and the extra 2D in the holomorphic direction will give me this spectral parameter. Yes. So I believe you can do similar things in 5D Chern Simons, but I'm not sure what exactly is. I'm not sure if we can find similar interpretation there.
Okay.
Yeah.
Okay. Is this sort of a thing somehow embeddable in holography? Is there a way that I can think of this W of Z as parameterizing some sort of torus that sits on top of my space as a modular parameter of some sort of torus by which I can then try to maybe couple, let's say, some ADS3 with some torus with some tau parameter and try to reconstruct this story?
I don't know. I'm not sure. I haven't think about this. Not sure.
Not sure it'll work. It's a chiral CFT.
Come again?
Not sure it'll work. It's a chiral CFT.
But you could make it not chiral by having 2 Chern Simons series, for example.
Well, sure. Sure.
Yeah. And then you can consider.
That's already an extension, though, what he's talking about, though.
Yeah, that's right. But I'm just asking.
Yeah.
Thank you. Any more questions?
May I ask you a quick question?
Sure. Yeah. Go ahead.
Okay. So you introduced the T operator in the beginning of the CFT part. And is there any relation to the G factor of this boundary CFT?
Oh, yeah.
The value of T gives you the G or this kind of relation.
So G in the sense of the free energy, right?
Yeah, it's a boundary contribution of free energy basically.
Yes. So the Wronskian I'm talking about is precisely that. Or you can think of this the VAV, the expectation value. So this is precisely the G function.
Okay, thank you.
Yeah.
Okay, if there are any more questions, let's thank the speaker for the really nice talk, and also let's thank all of the other speakers for the very nice presentation.
Thank you.
We'll stop the recording now, and then you can talk more